Okay, let's do one more example. Say the good folks at Kruger Industrial Smoothing are considering two different polishing machines, Machine A and Machine B, to purchase. One of the criteria they will use to make this acquisition decision is time between necessary repairs, measured in days. A sample of size 24 times to repair for Machine A was collected, and the mean time between repairs was found to be 55.6 days, with a standard deviation of 8.85 days. For Machine B, a sample of size 24 resulted in a sample mean of 67.9 days, with a standard deviation of 8.99 days. And what we want to know is this: does Machine B have a longer time between repairs than Machine A? And let's use the p-value approach to address this. Okay, so let's first talk about the sample that we collected. Okay, so we collected a sample of, from Machine A, we're going to call that population 1. We collected a sample of size 24. Okay, and the mean time between repair for Machine 1 from that sample of 24 was Y1 bar, which is 55.6. Okay, that's in days. And the standard deviation in days was 8.85. Okay. For Machine B, that is population 2, we collected a sample of also size 24. And it had a mean time between repairs, of 67.9 days, and a standard deviation of 8.99 days. Okay? And we want to answer a hypothesis. We want to know if the mean time to repair for mean time between repairs for Machine B is longer than that of A. So we call B population 2. We got to make sure we keep this straight, right? 1 and 2 are arbitrary, but once we make a decision, we've got to keep that going through the whole problem. Okay? We said that this was Machine B and this was Machine A. Okay? We want to know is the time between repairs for Machine B longer than A? Longer does not imply equality, okay? So we want to know, is B greater than A? All right? But we're using this notation, 1 and 2, so let's just keep that notation, okay? mu1 less than mu2 is the same as saying B is longer than A. Okay, if we go the other way, we're saying B longer than A. Okay, so let's just keep this 1 and 2 the same way, just so we don't confuse ourselves. But whenever we say is B longer than A, we're saying is mu1 less than mu2. Not an equality statement, so it can't be in the null. We know equality is always in the null. Okay, so this cannot be in the null statement. The contradiction of that, though, is in the null. That includes equality. Something like that. Okay? So the equivalent statement here is mu1 minus mu2 is greater than or equal to 0. And this equivalent statement would be mu1 minus mu2 less than 0. Okay? If mu1 is less than mu2, then Machine B has a longer time between repairs than Machine A. Okay? So now let's address this problem. Okay, this is a one-tailed test. Okay, one-tailed test. We need to figure out what these degrees of freedom are. Degrees of freedom here would be N1 plus N2 minus 2. That's 24 plus 24 minus 2, which is 46. Okay, so now we've got 46 degrees of freedom. And let's use the p-value approach here. So we need to calculate the test statistic. Okay, test statistic, again, y1 bar minus y2 bar minus mu1 minus mu2. Okay, how different is the sample evidence, the difference in sample means, different from the hypothesized situation in standard deviation units? N1 minus 1 times S1 squared plus N2 minus 1 times S2 squared over N1 plus N2 minus 2. Multiply all of that by 1 over n, square root of 1 over N1 plus 1 over N2. Okay? Just arithmetic. We've got everything we need. We just have to plug it in. Okay? Y1 bar is 55.6 minus 67.9. minus this hypothesized difference, it's just 0, in standard deviation units. Okay, that's 24 minus 1 times 8.85 squared plus 24 minus 1 times 8.99 squared, all over 24 plus 24 minus 2. And we're going to multiply that by 1 over 24 plus 1 over 24. Take the square root of that. Okay? So this is our test statistic. How different is the sample evidence from the hypothesized value in standard deviation units? Okay? If we work that out, we get something like negative 4.78. Okay? Negative 4.78 lies way down here. Okay? But what's the p-value? Okay, we want to use the p-value approach here. We don't want to just use the critical value approach. Let's use the p-value approach. Okay? So how do we look this up using the p-value approach or using Excel? Okay? We're probably not going to find 46 degrees of freedom in most t-tables that we might be looking at. Okay? So let's just use Excel for this because we can find that 46 degrees of freedom exactly. So we're going to use the t-dist function in Excel. Okay? Remember what the t-dist function wants. It wants a value on the axis, in this case our test statistic. Okay? Then it wants the degrees of freedom, and then it wants the number of tails that we're finding the area for. Number of tails. Okay? So how we're going to implement this is with t-dist. We're going to put in the test statistic. However, Excel does not like it if you put in a negative number for the test statistic. Okay? So we have to put in the positive number. Okay, but we can keep track of this. Okay, so what we're going to do is put in the positive number, and it's going to give us the upper tail, which is going to be the same as the lower tail because of the symmetric nature of this distribution. Okay, then the degrees of freedom. Degrees of freedom, 46. Then whether we want the probability in one tail or two tails. Well, we want a one-tail probability. Okay, this is a one-tail test in the lower tail. We're inputting the positive value of this, so it's going to actually give us the upper tail. But it'll be the same result. Okay, so whenever we input this into Excel, we get something like this. 9.16 times 10 to the negative 6. Okay, very small p-value. Okay, this is the p-value right here. Very small p-value, smaller than most any alpha you would ever choose. Smaller than 0.05, smaller than 0.01. Very small. Okay? So, since the p-value is smaller than alpha, we reject the null. Okay? P-value smaller than alpha, you reject the null, and conclude that indeed mu1 is less than mu2. So what that means in terms of our problem is mu1 is less than mu2. That means that machine A takes less, there's less time to repair. There's less time between repair than machine B. Okay? That means that machine B has a longer time between repairs than machine A. Okay? Machine B has a longer time between repair on average than machine A because machine A less than machine B. Mu1 less than mu2, therefore mu2 bigger than mu1. Okay? Machine B has a longer time in between repairs on average than machine A. And it actually, we can draw that conclusion with quite a high amount of confidence. Okay? This would be 99% confidence, and we could really have a lot more confidence in this result based on how small that p-value is.